you need to be looking at this example. Now, I filled it all out, and if you were in third hour, then you already had this information. So more second hour students are going to have to watch this part, and then we're going to continue on to the next section. Example 4. This is example 4 in the first group of notes over S1. This is an example of a 4-type problem for this standard. We start out just by reading through it and identifying what my X and my Y are. So the profit for shoe manufacturer can be modeled where X by this function where X is the number of shoes produced. So I said, okay, well X is the number of shoes, which means my Y is my profit. So even though they use P here, I'm just saying that's the same thing as Y. The company now produces 1 million shoes and makes a profit of 25 million, but would like to cut back production. What lesser number of shoes could the company produce and still make the same profit? What lesser number of shoes? This is what it's asking you to do. It's asking you to find other solutions when Y is 25. Okay, so we take 25, that's what we want my profit to be, so we plug it in. And then to solve for another value, I'm going to move it over so I get it equal to 0. And then I'm going to solve. They've already told me that in this equation here, when the profit is 25, my one of my solutions is 1 because it says 1 million. Oh, and the reason I'm using 25 is because this is written in terms of just 1, and they're just saying that represents 1 million, so I'm going to write 25 million. It's just 25, knowing it represents 25 million. Anyway, so then I plug in 1. So this becomes like the same thing we've already been doing. I'm looking for another solution. My first solution they gave me was 1. Plug in 1, go through the synthetic division. My remainder should be 0 here. And then I solve this using the quadratic formula. When you solve it using the quadratic formula, you end up getting, well, you get 2 answers. One's negative and one's positive. We want just the positive answer, which ends up being 0.7. So then we talk through, well, how can you get the same profit if 1 million shoes and 0.7 million shoes end up giving you the same profit? Well, the less shoes you make, the less materials you have to have, maybe even the less people you have to hire. So you're going to have more profit because you don't have as much expense. So even though you're not selling as much, you also don't have as much expense, so it balances out. So it is possible to have 2 different values that would give you the same output in a company. And that's important for a company to know, because if they're not selling 1 million shoes, they're selling 0.7 million shoes, and they know, hey, we're going to cut back, because I know if I cut back, I can still make the same amount of profit. Alright, so I know that was a lot of writing and a lot of talking. If you need to pause it to finish copying it down, go ahead. And you're going to get focused practice on this tomorrow. Alright, for standard S2, this is one we're going to focus on today. I can solve radical equations and determine extraneous solutions. I can apply this to simple story problems. And then for the 4, I can solve a radical equation that involves a radical on both sides. And I give you an example of what that might look like. I can write a radical equation that would have an extraneous solution. Alright, we're now going to get into our getting into our next set of functions called radical functions. To begin our discussion, we first need to talk about something we already know a little bit about: finding square roots and cube roots and what that means. It's the first question. When you find a cube root of something, what are we really doing? Well, when we find a cube root, we are trying to find what times what times what gives me the answer. For example, 2 times 2 times 2 equals 8. So 2 is the cube root of 8. When you find the nth root of something, what does that mean? Well, it means the same thing, except the n refers to how many of these you're trying to multiply to get the answer. So if I say take the 5th root, or the 4th root, or the 6th root, it just means you're trying to find that. Like if I said find the 6th root of something, you're trying to find what times what times what times what times what times what gives you the answer. So when you find the nth root, you are trying to find what times what times dot 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 what, I'll put n number of what's. If that makes sense, hopefully it does. So what times what times what times what, and it's going to keep going until you reach the number of n's that you have. So n being the fifth or the fourth or the sixth or whatever it's asking you to do. So the n number of what's to get the answer. For example, fifth root, n is 5, so what times what times what times what times what. Okay, so if you're looking for the fifth root of something, then your n equals 5, and so it's what times itself 5 times gives you the answer. So how do we know what root to take? The index, which is the small number from the radical. Now, why do we need to know this? Because we have to use this fact to solve these types of equations by hand. So an index here, like you've already seen them with a cube root, that's an index. Tells you to take the cube root. Or if I said take the fourth root, it would look like that. Just tells you what root to take. Now, before we get to solving, we have to talk about one more thing, rational exponents. Rational is a fancy word for fraction. So yes, that means you're going to have exponents that are fractions now. It's not scary as long as you know how to interpret what the numerator and denominator mean. Okay, so for rational exponents, you have, we'll go a to the m divided by n. This is what we would call exponential form because you're written as an exponent. But what this means is it's actually a radical. The n is your index. The m is your power. So I usually say, okay, that means power over index, and often we'll convert it back to its radical form because it might make a little bit more sense. Having something that's written as 2 to the 2/3 or 4 to the 2/3 or 8 to the 2/3 might make a little more sense if we wrote it as, and maybe we'll show an example. Let's do 8 to the 2/3. Writing 8 to the 2/3 would be the same as writing the cube root of 8 squared. Or the other way you can write it too is you could put the square out. So that fraction is power over index, the power, and then the index on the bottom. When you convert it to radical form again. Okay, so example 1, converting radicals to rationals and vice versa. We're just going to do 2 little examples here. First one I'll do with you. Second one I'll probably give you a little bit of space to do it on your own. So we'll go with 4 to the 3/4. Okay, if I asked you to convert that to radical form, the power would be 3, the index would be 4. So we have the 4th root of 4 cubed, or the other way that you can write it is that way. Either way. Okay. What about x to the 5/7? Okay, if we were to convert that, your index is 7. Power over index. And your 5 is your power. Or you can write it power underneath. Okay, so it's just converting back and forth. Really the only reason we talk about this is so that when you see an exponent that is a fraction, you know it technically is a radical, first and foremost. That those numbers mean something specific, like one is the power and one is the index. Okay, and flip. Alright, so we're going to go through steps to solving radical equations. The first step is to isolate your radical. I'm trying to think if I want to add anything there. Isolate your radical. And then parentheses. If you have two radicals, get one on each side. Okay, so isolate your radical. If you have two radicals, get one on each side. Then you're going to raise each side of your equation to the power that will cancel out your index. Okay, and we'll look a little bit further into that. And for number 3, solve for your variable. Alright. Let's go ahead and we'll do one example under example 2, and then we might split up example 3 into 2. Alright, so for this example, I have 3 times the square root of 3x plus 4 minus 5 equals 10. Okay, so the first thing we need to do is isolate my radical. It's like this is grouped together. I can't ungroup them unless I get rid of the radical, so I have to first isolate it. Excuse me. So we're going to add 5 to both sides. And then divide by 3. Now over here, the 3 on the outside is what cancels out. Can't cancel anything out underneath the radicals. That's all glued together. So this 3 just cancels out with that 3 out there. 15 divided by 3 is 5. And then normally, we want to do the opposite operation. So when you're trying to solve, you want to do the opposite operation. So we're going to square both sides here to get rid of the square root. Now technically, with a square root, your index is 2. It's just not written there. Okay, so square root cancels out the square, leaving you with 3x plus 4 equals 25. And then you just solve for x. So we're going to subtract 4 from both sides and divide by 3. And so you get x equals 7 here. Let me just double check and see if that works. When I plug in 7, you get 21 plus 4 gives you 25. The square root of 25 is 5. 5 times 3 is 15. 15 minus 5 is indeed 10. So yes, it does work when I check it. Okay, and then we're going to do 2 more examples here. Let's do just a simple, we'll do an A and a B here. Let's do a simple fraction one. Let's go 2x minus 5 to the 1/3 minus 4 equals 12. Okay. So with rational exponents like that, if you're uncomfortable using them, remember that when you see an exponent that is a fraction, what it really means is that it's a radical, and its power over index. So my index is going to be a cube root this time. And then it looks more similar to what we were working with before. So we're going to isolate my radical here by adding 4 to both sides. And then to get rid of the cube root, I need to raise it to the third power. So third power cancels out the cube root, and you get 2x minus 5 equals, oh dear, gets you 16 cubed, 4096. And then we're going to add 5 to both sides, and then divide by 2. Now since that doesn't reduce nicely, I'm just going to leave it like that. We can double check. If I was to plug that back in, here, the 2's are canceling, you get 4,105, or sorry, 4,101 minus 5. So 4101 minus 5 gets you 4096. Cube root of that is 16. 16 minus 4 is 12. So it does work out there. Okay. And then the other one that I want you to try, well, we're going to do really quick. Let's do 4x plus 5. We'll do the square root of that equals the square root of 5x plus 1. Now, if you have that situation where you have 2 radicals, you can't really isolate them because there's 2 of them, and they're different. So you set them equal to each other. Just make sure one's on one side, one's on the other. And then we're going to square both sides. When I square both sides, and the reason I chose to square is because these are square roots, cancels out, leaves you with 4x plus 5 equals 5x plus 1. Then we're going to subtract 1, subtract 4x, and you end up getting x equals 4. And if I was to double check that, here you'd get 16 plus 5, which is 21. Here you'd get 20 plus 1, which is also 21. So yes, the square root of 21 would equal the square root of 21. Okay, and then tomorrow we're going to do some more together on example 4 type problems.